Okay. So I'm so happy today to have Professor Ben Roth here. Hello, hello.
Do you want this?
Yeah, so I'm so happy today to have Professor Ben Roth here. And Dan is Eduardo Blended Distinguished Professor at UPenn. So he's also a fellow of AAS, HPI, and ACL. So in 2017, Dan was awarded the John McAfee Award. So this is a highest award that people can get when they're in the need. So in the award statement, Professor Roth was recognized for his contribution of conceptual and theoretical defense, modeling of a natural language understanding. So as you may know, Dan is my academic. I want to express how grateful I can have Dan as my advisor. You will hear our talk. So without further ado, let's just welcome Dan.
Okay, thanks, Kaiwei. Thanks all of you for coming. You can hear me well in the back? Really a pleasure to be here, and I had to think a lot about what should I talk about. In a place like this, I guess there is tradition of reasoning, so I wanted to talk about this, which is certainly an important part of the work we do. And I'll talk about this with a focus on natural language understanding. If I have time, hopefully we'll get to some bonus coverage. But I want to start by reminding you, those of you that read in the newspaper that AI is almost solved, maybe you need to train a couple more classifiers. I want to remind you of this interesting project. This is a project that was the PhD thesis of Terry Winograd at MIT about 50 years ago. The idea was to play with blocks. It was the block small domain and interact relative to the blocks and solve problems. Basically, build different things, move different things, and so on. And of course, the problem was solved there and then. Only that it's not working so well. So today we have this project, the DARPA project that is called Communication with Computers, trying to solve the same problem. The way we are looking at it, we have an architect that defines target to a program. Think about it as a Minecraft program. And we have a builder that tries to understand the architect and communicates with the architect in order to actually accomplish this task. You can see here on the right, hopefully this is readable, the type of interaction that architect and the builder beyond what we can do today in natural language processing. Now it's even better. Okay. But you could hear me without it, so should I say it again? Okay. So anyhow, so we are playing really Minecraft between an architect and a builder. The architect could be a human, the builder is supposed to be a machine, and the idea is to build something. If you read the language that is here, you may kind of figure out why this is so difficult. It's really beyond what natural language understanding can do today. And let me give you a simple instance that will illustrate this. So this was Terry Winograd's time. This is what we're trying to do today. And as a way to simplify the task even more, we've collected data. The data was collected by Jonathan Bisk when he was a postdoc at ISI. That is much simpler. Basically, blocks are on a table. In order to simplify the reference problem, which is really a difficult task, even today's NLP, we actually labeled all the blocks. So rather than say the second block to the right after the red one, we name them based on companies. And the goal is basically to place new blocks. For example, I need to move UPS from the left side of the board to just below Starbucks, leaving a small gap. So people are asked to describe this task in natural language. And then the idea is, can we understand it and actually execute this task? Here is an example, real example from one of the users. the user said this: imagine that this is a chessboard. Place the UPS in H2 and McDonald in G6. Now imagine writing a program before you see this input that solves this task, and now get this input, see what you do. Very difficult. You know, every 5 years old that knows something about a chessboard can do it. And if they don't, I can explain to them what's a chessboard in a couple of sentences, and they'll be able to do it. But we don't know how to do this in today's natural language understanding. We cannot follow these instructions. So, of course, I don't want to say that we haven't made progress. There's a lot of things that we can do in natural language understanding, mostly using machine learning techniques, more recently using deep network techniques. Mostly these are at the sentence level. We're not done there yet, but we are doing quite well. Mostly extraction tasks. But we have a lot of work in front of us. So today I want to give you some thoughts, optimistic thoughts about where we are and where we should go, and focusing on challenges. And I want to do it from the perspective of learning to reason, which I'm going to say a little bit about what it is, and really how should we think about learning in the context of reasoning. So let me start by telling you what I think about natural language processing, and I'm going to start with this example that you can all read. Some of you know it, but most of you don't. What does it say? Nice to meet you too. So everyone gets this, and people get it in seconds, you know. The slow one would get it in a minute, but everyone gets it. So to me, this is natural language understanding. So why do I think about this as natural language understanding? So what did you have to do here? I mean, really you had to identify units. You had to consider multiple representations of the units. You know, there's digits, there's pictures, there's characters. Each one of these units has multiple interpretation when in isolation. Maybe a distribution over these multiple interpretations. But when I put them all together on one slide and my behavior indicates that it means something, you all manage to put it together and determine the best, under some good definition of best, the best global interpretation, something that satisfies the expectation of all these put together on one slide. All these form a puzzle that has a solution. So to me, this is what we do all the time. Whenever you understand what I'm saying behind my fine accent, you do this kind of puzzle solving. When we communicate, we do this puzzle solving. So this is really natural language understanding. So natural language understanding decisions are global decisions that require us to make a lot of local predictions driven by different models, trained at different times, different contexts, different scenarios. They require us the ability to put together these predictions in a coherent way, and they require the use of knowledge that is going to guide these decisions so that they can satisfy our expectations. And these are really two key issues here, that we want to make coherent decisions and that we have expectations from the output, and these expectations guide what we're doing. So this is some kind of a thesis of the way I think about natural language interpretation, really as an inference process that you can best think about as a knowledge constraint optimization problem done on top of multiple statistically learned models. So really this is a reasoning problem that we have to solve continuously. So now, of course, today symbolic reasoning is no longer a term that you as students use, because we probably don't need to do any reasoning anymore. We can just evaluate neural networks. And in fact, to the extent that some people think that symbols is some evil invention of old AI people. It's not. Because language really is a symbolic system. So this table here is really a collection of things in the world. It means something. It's important that we name things. So even though we communicate via speech, gesture, you know, a lot of continuous processes, symbols are really the invariant of this communication, and we have to be able to, we need to have them, and we need to be able to reason with respect to them. So if you don't want to believe me there are some good philosophers and writers that have written a lot about this. So one of a book that I really like by Yuval Harari, *Sapiens*, talks about the ability to languages, the ability to assign symbols to things and reason about them, and argues that this is a key to the human cognitive revolution. My favorite philosopher, Sol Kripke, talks about naming things as a key to communication and to cognition. And I think, if you read this and think about it, you'll probably agree that we cannot forget about this aspect of AI and natural language understanding in particular. So a lot of us, when we do think about symbolic reasoning, we think about this guy. This is Aristotle. He founded the study of formal logic, and he's famous for this simple syllogism example: all men are mortal, Socrates is a man, therefore Socrates is mortal, which is really an easy thing computationally. But once you think about him, you can probably think about this question also. Did Aristotle have a laptop? Most of you actually laugh when I ask this question because it's trivial, and of course the answer is no. Now, by the way, if you Google for it, you'll get yes, because there's a book called Aristotle's Laptop. But this is a natural language question that you can answer instantaneously. And the question is, how do you think about it? How can we write program that will eventually, when faced with this question, will be able to answer this question? And I think this is really what we have to think about. So really the question is how to go beyond the way we think about natural language processing or machine learning today, where we have typically a well-defined task that we or you defined, collect the data for, and train a good model. That's fine. We know how to do it. We know that we can do this well. But who asks the questions? So in this specific Aristotle example, you probably develop instantaneously a strategy. Maybe the strategy was, when did Aristotle die? Let's think about it. Maybe you have some approximation. You don't really need to know exactly. When was the laptop invented? Which one happened first? So you have some simple temporal procedure to follow up on your strategy, and you can do it. So the question, I think, isn't whether we need reasoning. The question is rather how to do it, how to determine strategies on the fly. And of course, how to train for it, because when you make decisions, these decisions are built on things that you read, things that someone tells you, things that you maybe trained using examples. So what kind of training paradigms and how should we think as building blocks for reasoning problems? And really, the key question is, how can we supervise for these very sparse events? So I ask you a question that you were not ready for, and you can invent these questions on the fly, and in fact, you are solving these questions all the time. But these are sparse. You cannot train for these. How do we do it? So I'm not going to talk a lot about how to supervise this. This is part of another talk. But I do want to say that one of the key questions that we have to address here is that of, do we do everything together, or do we need to decompose things or decouple processes? Now, of course, AI over the years has thought a lot about reasoning. In most cases, when people thought about reasoning, they thought about it in a way that completely decouples knowledge representation and reasoning from learning, which perhaps is the reason reasoning counter react now. One exception is actually work that is 25 years old now for my PhD thesis, work that I've done with Ronnie Chardon, where we talked about learning to reason. So this work came up as a reaction, if you want, to the standard in AI at that time of complete decoupling of learning and reasoning. And the idea was to develop a unified computational theory of learning and reasoning. So one of the contribution at that time was to formally show the benefits of jointly studying learning and reasoning. And we actually worked within some formal models that were studied in computational learning theory and proved that there is benefit in doing this together. Now, of course, now these kind of approaches are called end-to-end, but better name. But what we failed to do, and I think is really important, is to add another question, which is studying when we need to decompose learning itself, the learning processes, and when do we need to decouple learning from reasoning. And these questions are very, very important, really at the heart of where we are today in terms of compositionality, reasoning, and transfer. And I think that there's no better domain to study this than natural language or natural language understanding. So let me start by giving, with a formal framework. One of the framework that one can use to study this is a model that we called about 10 years ago constraint conditional models. Really, you can think about it for as an abductive reasoning modeling for people that understand this term. We start with an objective function here, argmax over variables that we care about, y's, of this linear function where we think about x as inputs and y as variables we want to assign values to. I'm going to give a lot of examples for that as we go. And you can think about this phi of xy as features, as models, as neural networks, if you like. This is where the nonlinearity of the model comes in. And then you have w, which could be a linear function over models. A way to combine models together, you can think about it as a logical function over models. And then you want to add to this a knowledge component. Basically, information that you have, and I don't care how you got it, whether you learned it earlier or whether you learn it together or whether you brought it from home. And we think about it as constraints that could be soft or hard constraints. And again, you have coefficients here that are penalties for violating the constraints. And you have this function, c of xy, that you can think about as how far is y, the assignment to my variables, from my expectations. Think about the nice to meet you example where you wanted to assign values to each one of the variables. And whenever you tried an assignment, you thought about how far what you get now is far from what you expect to see. So this is a model that we can think about also as an integer linear program. Now, you don't have to think about it this way. You can think about this way if you like these forms because you like to think about convex function that you can differentiate. You can think about it in this way. But there are modeling advantages to sometimes think about it this way. The importance of this is not only in the modeling, but one other point is that either way you think about it, it's important that these phi of xy themselves, the variables that you care about, could be the models themselves. So there is a recursive nature to this that you can exploit if you like. The important thing here is that it opens up a lot of questions that you can ask, both in practice when you want to use it, and theoretically if you want to study this as a framework for learning and for reasoning. You can ask, what are the variables? How do I want to represent knowledge? So these are modeling questions. You can ask whether this is expressive enough for the types of problems that you want to study. And there are some things here that we know. For example, if you want to express your constraints as Boolean functions, any Boolean function that you like, this is expressive enough because we know that all Boolean functions can be represented as sets of linear constraints. In terms of the objective itself, we also know that it's quite expressive because every map problem with respect to any probabilistic model can be formulated as an ILP. You can also ask some computational questions. How do we do training here? Do we want to learn just the objective function, the vectors W and the vector U that you saw here? Or do we want to learn all the intermediate functions, phi of xy, or do we want to bring them from home or train them in other scenarios? Do we want to learn everything jointly, or do we want to decouple, for example, learning the constraints from learning the function? Do we want to treat the constraints as hard constraints or as soft constraints? There is some understanding over the years for these kind of questions, but there's still a lot of questions. And there's also the reasoning aspect here. So I think about reasoning, as I indicated before, as a way to push a function over learned models, which is what reasoning is, to satisfy output expectations. You can think about output expectation, you can think about expectations from a latent representation, but either way, you can think about how do I want to accomplish this kind of reasoning. Now, it's clear today that this formulation by itself is not enough. We need to deal with more expressive formulations, but this formulation has already been used quite successfully over more than 10 years in many, many natural language understanding tasks, from information extraction to parsing, to discourse tasks like co-reference resolution, to summarization. And really, it's a good framework to serve as a starting point to study and think about the interaction between learning and reasoning in the context, for example, of natural language understanding, as I'm going to do here. So let's go back to this temporal question. And what I'm going to do in the rest of this talk, or most of the talk, is I'm going to think about time, just like in this question, in the context of natural language understanding. So I'm going to use this framework that I illustrated before and a few other steps as a way to reason about time as it's expressed in natural language. Specifically, I'm going to focus on one temporal reasoning problem, and this is the question of temporal ordering of events. In this context, I'll be able to think a little bit about learning and inference paradigms to support this reasoning. I'm going to talk a little bit about acquisition of temporal common sense, and I'm going to talk a little bit about supervision paradigms that we need, advantages, disadvantages, and what we can do here. So clearly, what I'm talking about here is going to be far from being exhaustive, but it's going to, I think, let you think a little bit about, from the natural language processing perspective, it's a move from sentence level to a situation level, which is very important. I mean, we want to think about events or situations, not only single sentences. And from the learning and reasoning perspective, it will allow us to think a little bit about some of the important issues that have to do with supervision and with combining learning and reasoning. Okay, so let me now move to talk about temporal relations. And that's basically the problem I want to talk about. So here is a piece of newspaper that talks about some events that have happened apparently in Los Angeles. And I highlighted here events. All the events for the purpose of this talk are going to be event expressed by verbs. And my goal is to be able to understand the temporal relations between these. I want to know what happened before, what happened after, whether two events overlap or not. It turns out that this is a very difficult task. I'm going to talk a little bit about where we were on this until a couple of years ago. We have n events, so we have n square edges that we want to be able to label, and it's hard to do even labeling, manual labeling. But we have strong expectations with respect to the output, and I'm going to discuss this in more details. One expectation is transitivity. We know that if A is before B and B is before C, then A is before C. But we have other soft expectations that are maybe harder to write, but we have some expectation when an event happens for what could happen immediately after it and what might have happened before. We have at least some distribution. So let me start by talking about the importance of this. So here are two events. One of them, people were angry. Another one, police used tear gas. Now, it's important to know the order of this event. If this is the order of the event, people were angry and therefore they did something and police used tear gas. This is one interpretation. You can also think about it this way. Police used tear gas, people, and therefore people were angry. So, of course, the information about this is typically not made explicit in natural language. People will not give you time steps explicitly, but you expect to understand the text to the extent that you can tell the difference between these two things. So in some sense, this is the task that we want to be able to address here. So again, this is the sentence. And the important thing to understand first is that relations between events in a given paragraph are not independent. Right? So even in this case, understanding cascaded, ripping, and monitor requires you to understand the relations between the relations. And as I said, we want to be able to translate it to this kind of graph. The task is really to label the edges of this graph. State of the art as of 2015 or so was low 50s F1. So basically, we cannot do this well. And this is when the events are given to us, which is the scenario that I'm going to deal with most of this talk. So it's a really hard problem, and the question is why. So the first thing, the first observation, as I said, is that there's transitivity, and transitivity should help us to understand something. So if I've annotated or have a model that labeled some of these edges, I should be able to say something about these other events. So for example, because ripping overlaps or is included with cascaded, and cascaded is before ordered, ripping also must be before ordered. So this is something that my model should be able to satisfy. So that means that I have to do some kind of global inference over outputs of models. So if my model, for example, is able to predict values for edges, maybe my model is something like this, and it gives me two options for each one of the edges between monitor, cascaded, and ordered, I should be able to relate them. So rather than just taking the mode in each case, taking the highest value, which results in a non-feasible graph, this cannot happen. I want to be able to consider many models. I'm showing here 3 options of models. Each one of them has a score as a function of the output of my local models. Each edges has a score, and I should be able to select which of these global assignment to the triples makes more sense. I want to not only choose the one that scores the highest, but also the one that doesn't violate our constraints. In this case, I'm only talking about transitivity. So again, this can be formulated using the formulation that I presented before, the ILP formulation. It's actually very easy. What I'm going to have is I'm going to have a linear objective function that you see here at the top, subject to some constraints. So I have Boolean variables that are my variables. What is the assignment of each edge that I show here, whether, for example, event I is before event J, or event J is before event I, or included, and so on. And I have coefficients that are real values, numbers that come from my local models. And in addition, I have constraints. So I have various types of constraints. The first one is just a syntactic constraint on the left that basically says that each pair of events is going to have one relation between them, not several. And the second one is the transitivity constraint, which if you think about it for a few seconds, you'll agree with me that this is indeed representing transitivity. So hopefully you agree with me now that global inference is essential, but how should we train these models, the R of ij? So you can think about training them before we even start independently, or you can think about the second step, which is think a little bit about it, and you see that local learning in this case is not sufficient. So let's take this example where I'm thinking about the events ripping and ordered, and I want to ask, what is the order, the temporal order between ripping and order? It turns out that you really have to think about it, because if that's all the context I give you, it's not completely clear what it is. You really need to be able to look also at another mention in this paragraph, mention of cascaded, because if you are not, your model is going to be biased. biased in the following way. Let's assume that I've annotated the sentence or the relation between reaping and ordered to be before. You're going to train the model to say before in this context, even though there's really no evidence in this sentence that this is before. So you're biasing the model in the wrong way. You really need to be able to give your model also information about what is the relation between cascaded and reaping, and what is the relation between cascaded and ordered for the model to be justified in classifying reaping and ordered to be before. Basically, that means that we need to do joint training of a lot or all these variables I of R, IR of IJ that we care about. This is what we call structured learning. So that's kind of the second step. So I talked about needing to do global inference over multiple decisions, multiple variables. And here I talked about the need to actually learn these multiple models together rather than independently. And the third component that I want to bring up is this one. So let's look at this piece of text here that says more than 10 people have, police said, a car, event 2, on Friday in a group of men. So if I ask you which one came first, event 1 or event 2, I think it's going to be difficult for you. So I don't give you the name of the event, but I'm just asking you which one comes first. Difficult. How about now? It has to be easy now. And the reason it's easy is because you have a lot of prior knowledge that helps you make the decision. Context itself is often insufficient. So the question is, how do we gain these constraints, this ability to use priors on this? So we would like to acquire this. So this is my third component here. So we need to be able to identify some temporal relations and learn something about these prior. What we've done in this case, we basically ran our initial system that had no common sense on a lot of newspapers, extracted events. In this case, I'm adding the extraction component that I skipped before, used our system to identify temporal order between them, and took a lot of statistics. And what you can get is information that is kind of very interesting. So if you look at the event ask and help, in all the cases where ask appears in the text before help, 86% of the time, it's temporally before. On the other hand, if you look at attend and schedule, of all the times attend appears before schedule in the text, in 82% of the times, actually, temporally schedule is before attend. And you can collect this for a lot of events, a lot of pairs of events. Essentially, for every event, you want to be able to learn or acquire a distribution of what might happen after the event and what might happen before the event. And here are some examples. So if you look at investigate, you can look at what events happen frequently before investigate and what events happen frequently after event. You can look at grant. This is something that will appeal to the faculty here. Before grant, you have seek and request and write. After grant, you have use and pay and work. So makes sense. So this is the type of information that you are able to acquire. Now, this is not the only common sense or temporal common sense that you want to be able to collect. There are many other types of common sense, temporal common sense. So this is an example. So I want to be able to know typical time of things. What you see here is work that will be in ACL this year, where we actually are able to determine typical time for breakfast, brunch, lunch, and dinner, or distribution over these typical times. And you want to be able to identify typical duration of various events and so on. But I'm not using this type of common sense in what I'm going to say next. I'm only going to use order between events. So in order to make use of this order between events, we're basically looking at it as a prior probability for each pair of events, Vi and Vj, And then in the learning stage, we can use these as features for our models. In the inference stage, all I have to do is basically I have to add this to my objective, regularize this. And in this case, what I'm adding is really soft constraints into my model. Okay, so basically so far, I talked about a few things that have to do with reasoning about time in natural language. I talked a little bit about temporal ordering, learning and inference paradigms that support reasoning, and the acquisition of temporal common sense. But I want to move forward and put it all together. So a lot of the things that I talked about before, I could have talked about 10 years ago, or at least 5 years ago. But you can put everything here into some more modern architecture that, in fact, nothing has changed really, modulo the fact that we have slightly better classifiers. So we can put it into an architecture that has an LSTM that basically does the structure learning for us, and that feeds into a feed-forward network, on top of which we are actually imposing the ILP constraints, and that's actually quite important. And what you see at the top here on the right is the way to incorporate common sense constraints into this framework. The important thing here is that we want to be able to not only incorporate common sense constraints, but actually generalize to events that maybe are too sparse and we haven't seen them, but we deem them similar enough to events or pairs of events over which we actually have a lot of data in our common sense priors. So we can put this architecture together. As I said, nothing really has changed beyond implementation. These are the same kind of learning and global inference ideas. And it's important to realize that both in the case of the common sense incorporation and the case of this feed-forward network that actually makes the final decisions, we had to be able to use constraints on top of it as a way to actually make sure that our decisions make sense. So altogether, actually, a lot has happened in these 5 years. So the results of our ability to identify temporal relations from 2015 to today, 2019, is really a semi-revolution in this. So we started with systems that could do about 50% F1, and today we are close to 80% F1 with various steps or multiple steps that all basically describe the key aspect of it. All have to do with how to think about learning, how to think about reasoning, how to put things together. There's one step that I skipped because it doesn't fit so nicely in my story of how to do global reasoning, how to do global learning, and how to add constraints. And I'm going to just say what it is. And this is the idea of rethinking a little bit the notion of relation between events. We call this multi-axis view of events. And really the observation is that you cannot compare all pairs of events because events reside in multiple axes. Some of them are real events, like tried and killed, and some of them are just intentions. So you, in this case, they try to eliminate and they try to restore. You don't know whether this was successful or not. So while you can compare events within each axis, you may not be able to compare events across axes. So what we've done, once we've made this realization and we defined several axes, I'm showing 2 of them here, was to basically re-annotate a lot of the data that was there to respect the fact that some events cannot be compared. We got less data than we had before, but we got higher quality training data, and that resulted in significant improvements and with the nice graph that I showed before. Okay, so now that we are done with understanding temporal reasoning, there is one other thing that I want to attend to, which is very important, which is the kind of supervisions that we can get. So really our goal here is to induce semantics. And we all agree that in most cases, inducing semantic representation, making decisions that involve semantics require some supervision. So today, the only way we are doing it is we define a task, we collect data for this task, and we annotate it. And then we learn a model. Doesn't matter how you learn the model. So I think that this is not enough. We will never have enough annotated data to train all the models for all the tasks that we need this way. And in fact, I don't think we even know what are all the tasks. It's not true that every complex task that we want to address, we can decompose into a collection of classifications of this sort. So really most of what we learn, we don't learn by training on many examples. So really we need to think beyond this current methodology that isn't scalable. And the framework that I'd like to think about is something that I'm calling incidental supervision, which I'm not going to talk about today. But what I want to talk about is one instance in the context of temporal relation extraction of this framework, because this instance is going to allow us to think about this very interesting aspect of incidental supervision. And here is what I mean. So let's go back to this paragraph that we discussed before and the temporal graph, and realize that it's very difficult. There's a lot of annotation that people have to do if we want to be able to train models for this, n square for every event. And people find this very difficult. What people find easy is to annotate it partly. You know, here is a pair of events I know the order for. Here is another pair of events I can tell you the order, and so on. So they give me some incidental evidence of what they know, but definitely not exhaustive. So the question is this enough? Now remember that I also have strong expectation that I exploited before, both hard expectation in transitivity and soft expectation in some understanding of what might come before and what might come after. So with these two, I want to be able to talk a little bit about what level of supervision do I really need in order to address this problem. And I'll argue, of course, that I don't need exhaustive supervision. And there's also an algorithmic approach, how do we gain from this, which I'm not going to talk about. So the intuition that I want to deliver in the next 5 slides is, if this structure is tight, in the sense that knowing some of the facts, some of the edges, gives me a lot of information about others, then I probably don't need exhaustive annotation. It's sufficient for you to give me a few hints, and I'm going to be able to learn from it. So I want to be able to quantify this, and the way to quantify it is to think about the following kind of game. So let's assume I have 2 paradigms. I have on the left a complete annotation scheme. So I have some budget. This is the number of edges that you're allowed or you can annotate. And I can either do it on the left side by annotating complete graphs, but not all the graphs that I have, or I can just annotate subgraphs here and there, but then I'm going to touch more graphs. So what you get from this is clear win for the partial annotation. Without giving you details of what this, higher is better. I'm going to get much better results in this case by annotating more graphs, and each one of them partially, relative to complete annotation with the same budget. And I want to give you the intuition for why this is so. I have to define what I mean by structure. Structure is just a collection of variables. You already saw it from the beginning of the class. And then I want to think about all the labels that are possible over these D variables, Y1 to YD. And of course, not all of them are feasible. So I'm denoting this with this C, constrained output space. Now, I'm defining this notion of the size of the feasible subset as a function of K, which is the number of labels I'm going to give you, the number of edges I'm going to label. Fk is going to be the size of the feasible set, the number of remaining options for labeling the rest. So, for example, if you're looking at this graph, I already labeled a few of the edges, and all I have now is 2 other options, either 1, 2, 3, 4 or 1, 3, 2, 4. No other feasible options exist. And the third definition that I'm going to have is this notion of Ik, which is the important one, which really measures how much of the feasible set has been disqualified once I gave you k labels. And of course, you want this to be disqualified very fast as k grows. That's the goal. And again, the same intuition. If the structure is tight, the larger k is, the faster the size of the feasible set is going to go down. And indeed, what you can see is that this ik, which really is the benefit that I get from k labels, is a concave function. And therefore, when I look at ik minus ik minus 1, I get that the benefit of a new label is diminishing. So once I gave you a few labels, I don't need to give you a lot more. I'm not going to gain from giving you a lot more. And you can look at this in a variety of problems. And indeed, you can see that this intuition holds. The tighter the problem is, the faster this curve goes down. And you can look at it at multiple problems or multiple graph structures and see that this is indeed the case. The more interesting one from our perspective here is the one on the top right, where temporal graphs are very tight, and therefore I'm going to gain a lot by not giving you a lot of labels, just a small number of labels from each graph. So indeed, when the structure is tight, there is no need to give you a lot of labels. Now, we can actually think about it a little bit more theoretically, and I'm not going to give all the details, but you can think about ik really as the mutual information between y, the set of labels that I care about, and ak, which is a process of labeling this graph. And this mutual information basically gives me an idea of how to think about it in a more general way, right? So rather than just thinking about it as partial assignment, because I think about it now as mutual information, I can think about my annotation process as any signal that has some non-zero mutual information with y as an annotation. So if you have some hints that are correlated with your labels, you can actually use them as annotation and exploit it. So really this points out a way to understand and quantify the value of indirect supervision signals in this annotation process. And the bottom line is that this is an important way for us to think about how do we get away from these exhaustive annotation things and move into what I call incidental supervision, just weak signals that are correlated with the labels that we care about. Okay, so basically, I talked about temporal reasoning, and I started with this Aristotle example. Unfortunately, we don't know how to solve this yet, but we have a recent paper where we actually define a challenge set for common sense or temporal common sense understanding. And we develop a lot of problems like this. We develop also some baselines where we can sometimes reason about these kind of problems. As I said, we can't solve the Aristotle problem yet. But building on the ideas that I talked about before, we can actually do something here. So I want to conclude now. And given that I have a little bit of time, right? I want to give you one bonus coverage. So I'm going to conclude this talk, tell you what I talked about, and then spend 3 to 5 more minutes talking about a completely different topic that I want to get you interested in and I think is exciting. So what I did in the last 50 some minutes is really gave you a small sample from a research program that we run in my group that attempts to address some of what I think are the key scientific and engineering challenges between us and understanding natural language. I really focused on temporal reasoning. It's not the only thing we have to do, but this allows me already to think about reasoning, to decouple or not to decouple, and supervision. How can we think about, or should we think about learning when we actually want to be able to do reasoning. So I talked about two of these examples, and I want to move on to, thank you, I'm going to come back to this, but I want to move on to my bonus coverage. So I talked about temporal reasoning, but there are many, many other applications of inference in natural language understanding. And one of them is a large project that we've been working on for the last year or so, which is what I call information pollution. I think all of you should be interested in this topic. So the introduction is that, you know, we all thought when information technology started that everything is going to be good. We're going to democratize access to the world's information. It's going to have huge impact on education, medical care, science, public policies. Everything is going to be beautiful. But really what we got is a lot of information pollution. I mean, I define here, or I follow a definition of Orman of information pollution as the contamination of the information supply with irrelevant, redundant, unsolicited, incorrect, and otherwise low-value information, which is something we see all the time when we try to search for anything on the web, medical information, educational information, not to mention news, and so on. So what should we do? So I think the problem is not that of factual information. I think the problem is beyond that, because most interesting questions do not have a single answer. They have a range of potential answers, and we want to be able to exploit this. So our approach is twofold. Has to do with studying the evidence, understanding what people are saying, and trying to understand them as perspective with respect to a claim, and understanding the sources. And our the key step that we've done so far is thinking about discovering diverse perspective. So this is a data set that will be presented in NACL. And what I'm going to show you now is, instead of talking about it, is a short video that talks about our system that solves, or at least does make some progress toward presenting perspective with respect to claims. One caveat that I want to mention before I say video, we use the word classifiers in the context of the video. Really, the problem is not a classification problem. The problem is what we call textual entailment, or various forms of textual entailment. It was easier to say this way in the video, so I'm going to give you, I think, a 2.5 minutes video. Let's see if that works. It's not working, huh? You don't see it.
Well, one key consequence of the information revolution is a significant increase in contamination.
Okay. 1 second. Yeah, I'll just move it somewhere. Oh, okay. Now you'll see it. Okay, let's see, how do I do it?
One key consequence of the information revolution is the significant increase in contamination of our information supply. Over time, this has resulted in radicalizing effects in our societies. Many entry points to information, such as search engines or social media, are over-personalized to reflect our existing beliefs. As a result, many of us are trapped in bubbles of like-minded groups. We only interact with and hear those who we tend to like. This is especially true with respect to many discussion-worthy topics, where there might be multiple valid aspects to the problems, and all of these views could be reasonable under different worldviews. In this work, we present Perspectroscope, a web-based system which lets users query a discussion-worthy natural language claim, and it visualizes different arguments with respect to the input. The system lets users explore various perspectives that could touch upon an aspect of the topic at hand. Suppose you are curious about various aspects of using animals in lab tests. So, you issue a claim to the system. Animal testing for medical research should be allowed. The system comes back with a range of perspectives, each with a stance relative to this claim. On one hand, there are various arguments that oppose the claim. For instance, by citing the cruelty of such tests and the suffering that they incur on animals. And even further, such tests on animals don't necessarily guarantee good results on humans. On the other hand, there are also arguments in support of this query. Using animals as test environments could be a necessity for developing certain medications. Such tests sometimes can save human lives. Essentially, each of these perspectives are opinions possibly in support of the given claim or against it, and thus they constitute a particular attitude towards a given claim. More broadly, by viewing the world as perspectives, the goal is to give the users the understanding that each story is not black and white, but really it has more than one perspective. And by going towards such representation of the ideas, we want to help individuals become more open-minded about learning views that they don't necessarily agree with. Let's take a different example. Social media, like Facebook or Twitter, have had very positive effects on our lifestyle. Again, there is no single way to respond to this query, but rather there are many responses that form a range of perspectives, each with a stance relative to this claim. To support this input claim, one could refer to the observation that interactions between individuals have become easier through the social media. On the contrary, one could oppose the given claim by pointing out their negative impacts on productivity or the increase in cyberbullying. Our system is built via a combination of retrieval engines and learned classifiers to create a good balance between speed and quality. Retrieval engines are used to quickly select candidates for perspectives and evidence documents. These documents are retrieved from a pre-compiled pool of documents as well as Wikipedia content. And the learned classifiers make the final fine-grained decision-making on the given set of candidates. Additionally, our system is designed with the mindset to get feedback from users of the system. A user could give us feedback about whether a perspective is relevant or not, whether a stance is correct or not, etc. It's important to note that we have not completely solved the problem. For instance, our system could make mistakes on retrieving relevant perspectives. And all of these happen because, of course, natural language is extremely complex with various exceptions, which makes it difficult for machines. Beyond this, there are algorithmic components that we have not addressed here and are opportunities for future work. For instance, the system provided here does not provide any guarantees in terms of the exhaustiveness of the perspectives in the world. We hope that some of these challenges and limitations will be addressed in future work.
Okay. The important stuff. Okay, so thank you, and I'm happy to take questions on this or on the video. So what's behind symbol is definitely contextual. Yeah. Yes, the answer is yes, they are contextual. I think. So I mentioned at the beginning, I mentioned this work that we are doing. And in the context of this work, we are doing a lot of spatial reasoning. So basically, one of the, so it has two components. One of them is this interaction with respect to physical things, placing physical things, understanding where they should be and so on. And also trying to understand spatial relations. What does it mean for something to be to the left of or to the right of? What does it mean for a man to be walking a dog? What is the relative position of a man and a dog when you say it? Or what does it mean to be sitting on top of a bed versus sitting under the bed and so on? So we actually are trying to look at it in a project that basically combines natural language with images in order to make progress on this problem. Thank you.